All right, let's dive into something you might not think about every day: purification. And I'm not just talking about, cleaning stuff. For a scientist, being able to pull one specific thing out of a messy mix, well, that's everything. It's the starting point for some of the biggest discoveries out there. So let me ask you this. You see a label that says 100% pure. We see it all the time, right? But is that really possible? Can something be absolutely 100% pure? From a scientific point of view, that question is a lot trickier than you might think. And that right there is the big problem. See, out in nature, or even when you're making something in a lab, nothing starts out pure. It's always a jumbled, messy mixture. You've got your main thing, but it's mixed with all sorts of other gunk. For any chemist, that's always square one. So, why do we care? Well, it's simple. You can't really understand something or use it or even figure out what it is until you get it by itself. You've got to separate it from all the other background noise. And here's the kicker. Even a tiny, tiny little bit of the wrong stuff, an impurity, can change everything. In medicine, it can make a drug not just ineffective, but dangerous. In our food, it can mess with the taste or even make it unsafe. So yeah, this whole quest for purity, the stakes are really, really high. Okay, so how do scientists actually clean up this molecular mess? Well, they've got a whole toolbox full of tricks. Let's pop the lid on that toolbox and check out some of the coolest ones. First up, we've got distillation. This one is all about a super simple idea: boiling points. Imagine you have a mix of liquids. The one that boils at the lowest temperature is going to turn into a vapor first. If you can just grab that vapor and cool it back down into a liquid, boom, you've separated it. And this is what it looks like in the lab. You heat the mixture, and the liquid that's most eager to escape, the one with the lowest boiling point, turns to vapor. It travels up and over into this cool tube, the condenser, which turns it right back into a pure liquid that you can collect. Pretty clever, right? But wait, what happens if the boiling points are super, super close? That's a tougher problem. For that, you need the heavy-duty version, fractional distillation. It's basically the same idea, but with this special column that acts like it's doing thousands of tiny little distillations all at once. It's incredibly precise. And this isn't just a lab trick. This is the massive scale process that turns crude oil into gasoline and all the other fuels we use. Okay, that's liquids sorted. But what about solids? A lot of the time, the answer is crystallization. And you actually know how this works already. Think about it. You can dissolve a ton of sugar in hot coffee, but not so much in iced coffee, right? Well, crystallization takes that exact same idea and uses it as a purification tool. So let's say you've got sugar mixed with salt, a real mess. But you find a liquid, let's say hot ethanol, where the sugar dissolves like a dream, but the salt just sits there. Step 1, you filter out the salt. Easy. Now you've just got sugar dissolved in hot ethanol. As you let that solution cool down, the ethanol suddenly can't hold on to all that sugar anymore. And what happens? Pure sugar crystals start to form, crashing out of the solution, leaving any leftover junk behind. Okay, but what about the really, really tough mixtures? The ones where everything is so similar, it seems impossible to separate. That's when chemists bring out the big guns, a technique called chromatography. And the name is actually super cool. It comes from the Greek words for color and to write. Why? Because it was first used to separate all the different colored pigments you find in plant leaves. So the inventor was literally writing with colors. How cool is that? The easiest way to get your head around chromatography is to picture it as a race. You have the racetrack, that's called the stationary phase, and then you have a liquid, a solvent, that flows over the track. That's the mobile phase. You put your mixture at the starting line, and the solvent just washes everything along. But here's the magic. Some parts of the mixture love to stick to the track, so they move really slowly. Others don't stick at all and get swept along super fast. And just like in any race, this difference in speed is what separates everyone out. And you can set up this race in a couple of different ways. On the left, you see column chromatography, where the racetrack is packed inside a tube. On the right is thin layer chromatography, where the track is just a super thin coating on a little glass plate. They look different, but don't let that fool you. The basic idea, the race, is exactly the same. All right, so you've done it. You've separated your mystery compound, it's nice and pure, but what on earth is it? See, getting it pure is only half the battle. Now you have to figure out its identity. And that analysis really comes down to two big questions. The first is qualitative. What is in this thing? Are there carbon atoms, hydrogen, nitrogen? And the second question is quantitative. How much of each thing is in there? We need to know the exact recipe, down to the percentage.
So to figure out the what, chemists have all these clever little tests that are like fingerprints for different elements. One of the most famous is the test for nitrogen. You run the test, and if your sample turns this brilliant, deep Prussian blue color, bam, you know for sure you've got nitrogen. It's a fantastic visual clue.
Now for the how much part. Scientists use some really smart methods, like one where they carefully burn a sample and measure what comes out. By doing that, they can calculate the exact percentages of elements like carbon and hydrogen. And what you're seeing here is the final result of a test like that, a perfect breakdown of the elemental recipe of the compound.
Okay, we've been geeking out about a lot of lab stuff, I know. But it's so important to remember that none of this is just for fun. These techniques are, and I mean this literally, the backbone of our modern world.
Just think about chromatography. Where is it used? Everywhere. It's how we make sure our medicines are pure and safe. It's the silent guardian in the food industry, checking for nasty chemicals or contaminants. It helps us find tiny traces of pollution in our air and water. And in medicine, it's used to spot signs of disease in blood tests. It is a true game changer.
So, next time you see that 100% pure label, maybe you'll think about it a little differently. You'll know about the incredible amount of science, the distillation, the crystallization, the chromatography that goes into that simple claim. This quest for purity, it's not just some boring lab work. It's a hidden, powerful force making our lives better and safer. So I'll leave you with this. What part of your world is pure, or safer, or just plain works because of these invisible cleanup processes?